33 trillion kilo. That's the minimum mass astronomers are now attributing to our latest interstellar visitor, 3I Atlas. To put that in perspective, it outweighs the Empire State Building by a factor of 40,000. Yet this cosmic heavyweight glides through space, producing active gas jets while showing virtually no orbital nudge from its own exhaust. It's like watching a freight train powered by birthday candles. But that's not even the weirdest part. Given its size, we should have found dozens of smaller objects before discovering such a giant. We didn't. Either our understanding of cosmic debris is fundamentally wrong, or we're witnessing something that challenges the very nature of what drifts between the stars. Tonight, we examine the discovery that may be rewriting the rules of interstellar archaeology as we face an uncomfortable question. What else haven't we discovered yet? Part 1. The Shockwave Announcement. New analysis claims 3I Atlas is at least 33 billion tons, with a nucleus 5 kilometers or larger, orders of magnitude above previous interstellar visitors. If that holds, our picture of interstellar debris just snapped. The numbers come from Harvard's Center for Astrophysics, where researchers processed 4,022 positional measurements from 227 observatories worldwide. This isn't speculation anymore. It's a lower limit, and it's preliminary. But the implications are staggering. Let's step back from the math for a moment. Astronomers saw virtually no measurable non-gravitational rocket push from outgassing. The limit sits below 15 metade2, or 10 nanze-2. When you convert those units, you're talking about forces so small they barely register above measurement noise. But here's the puzzle. Weak push plus visible activity equals big mass, very big mass. The rocket effect is simple physics. When a comet gets warm, ice sublimates into gas. That gas escapes, creating jets that nudge the comet like tiny thrusters. We've seen this countless times, but 3I Atlas shows active outgassing, water vapor, carbon dioxide, even exotic compounds. Yet the expected nudge isn't there. The only explanation that fits is mass. Lots of it. Why does this matter? Oumuamua showed anomalous acceleration that puzzled scientists for years. 2I Borisov behaved like a textbook small comet, reassuring in its familiarity. 3I Atlas introduces something new, a heavyweight that acts like an active comet, but shrugs off its own breath like a mountain ignoring morning mist. We're looking at a regime we've never seen before. The community reaction has been fascinating to watch. Astronomers express curiosity mixed with healthy skepticism. The coverage summarizes the mass limit narrative accurately, but everyone stresses this hasn't undergone peer review yet. It's extraordinary claims meeting ordinary scientific process, exactly how it should work, but the tension is palpable. You can feel the field holding its breath. Let's establish what we know for certain. This is the third confirmed interstellar object ever detected. Atlas discovered it on July 1, 2025, from their facility in Chile. The Minor Planet Center officially designated it C2025N1 Atlas, but everyone calls it 3I Atlas. The 3I means third interstellar, a reminder of how rare these visitors are. Before anyone asks about planetary defense, Earth is perfectly safe. Closest approach to our planet occurs December 19, 2025, at about 1.8 astronomical units. That's roughly 170 million miles, closer than some asteroid approaches, but still comfortably distant. We're observers, not targets. The visual evidence tells its own story. Hubble captured 3I Atlas on July 21st, revealing what astronomers describe as a teardrop-shaped cocoon with an unusual sunward glow. Most comet tails point away from the sun, pushed by solar wind and radiation pressure. This object showed a forward glow, an anti-tail pointing toward our star. That's not unprecedented, but it's uncommon enough to raise eyebrows. By August 27th, though, Gemini South telescope observations showed the anti-solar tail growing more pronounced. The morphology was evolving as the object warmed, painting a picture of complex dust dynamics and gas flow patterns. Each image became another piece of evidence in the mass puzzle. Here's what makes the numbers so jarring. If 3I Atlas really has a 5-kilometer nucleus and weighs 33 billion tons or more, it's 3-5 orders of magnitude more massive than 1I Oumuamua or 2I Borisov. That's not a modest upgrade. That's jumping from pebbles to boulders in the cosmic debris field. Population statistics suggest we should find smaller interstellar objects first. They're easier to eject from their home systems, more numerous, and require less energy to accelerate to interstellar speeds. Yet here we are, 3 visitors in, and the latest is potentially the largest by far. It's like discovering mice by finding elephants first. The mass estimates depend heavily on assumptions about outflow rates and gas velocities. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, providing crucial spectroscopic data about what's actually sublimating. Those measurements inform the models that connect visible activity to invisible mass. But models are only as good as their inputs, and right now, those inputs are still being refined. JWST's infrared spectrograph detected water ice, water vapor, carbon dioxide, and carbon monoxide. The carbon dioxide to water ratio ranks among the highest ever measured in a comet at this distance from the Sun. That suggests formation far from a parent star, beyond what astronomers call the carbon dioxide snowline. Regions so cold that carbon dioxide freezes solid alongside water. The chemistry adds another layer to the mystery. Most comets this far from the Sun show different volatile signatures. 3I Atlas seems enriched in compounds that require extreme cold to condense, painting a picture of birth in the frigid outer reaches of some distant solar system. It carries the chemical fingerprint of alien ice. But let's maintain perspective. The numbers pushing researchers toward silent giant status rely on preliminary outflow rate estimates around 150 km and gas velocities near 440 ms. These are model-dependent values that will be refined as more analysis is published. The JWST team hasn't released their definitive measurements yet. Still, the basic physics is hard to argue with. If you see active gas production, but no measurable rocket effect, something has to give. Either the gas isn't escaping efficiently, which seems unlikely given the visible coma, or the object is massive enough to absorb the recoil without flinching. Current evidence favors the second option. The visual metaphor writes itself. Imagine a person trying to move a freight train by throwing tennis balls at it. The balls bounce off, the train doesn't budge, and observers realize they're dealing with something much more substantial than appearances suggest. 3I Atlas appears to be the freight train of interstellar objects. This raises uncomfortable questions about our understanding of the galactic debris field. If massive objects like 3I Atlas are out there, where are all the smaller cousins we expected to find first? Are they invisible to current surveys, destroyed by interstellar erosion, or simply much rarer than models predict? The stakes extend beyond academic curiosity. The upcoming Vera C. Rubin Observatory will scan the southern sky every few nights, potentially discovering dozens or hundreds of interstellar objects annually. If 3I Atlas represents typical visitor mass rather than an extreme outlier, our entire framework for understanding planetary system formation needs updating. So, what evidence pushed researchers toward this silent giant hypothesis, and can we trust it? Part 2. The Silent Giant. The evidence forms a compelling trilogy. First, an upper limit on non-gravitational acceleration, so small it barely registers above zero. Second, visible cometary activity captured by multiple observatories and space telescopes. Third, an unusual carbon dioxide-rich chemistry profile from JWST that stands out among solar system comets at similar distances. Let's unpack the rocket effect in simple terms. Picture a garden sprinkler spinning as water shoots from its arms. The escaping water creates tiny forces that make the sprinkler rotate. Comets work similarly. Jets of sublimating ice create small but measurable pushes that alter orbital trajectories over time. Astronomers have detected these non-gravitational accelerations in hundreds of comets. It's routine physics, but 3I Atlas breaks the pattern. Despite clear evidence of outgassing, water vapor streaming away at hundreds of meters per second, carbon dioxide creating an extended coma reaching hundreds of thousands of kilometers, the expected orbital nudge simply isn't there. The acceleration limit sits below 15 mph, essentially indistinguishable from pure gravitational motion. Compare this to 1I Oumuamua, our first confirmed interstellar visitor. That enigmatic object showed measurable non-gravitational acceleration without any visible cometary activity. The opposite problem. Scientists proposed various explanations, from hydrogen outgassing to solar radiation pressure on an unusually elongated shape. The debate continues today. 2I Borisov provided reassuring normalcy. Discovered in 2019, it behaved exactly like solar system comets of similar size. Spectroscopy revealed familiar water and carbon monoxide emissions. Its nucleus measured roughly 1 kilometer across, and the non-gravitational acceleration matched expectations perfectly. Borisov was comfortable, predictable proof that interstellar comets could behave just like homegrown ones. 3I Atlas occupies a different region of parameter space entirely. It shows the activity expected from a comet, but rejects the physics that should govern that activity. It's like watching someone swim through water without getting wet. Logically impossible unless fundamental assumptions are wrong. The chemistry adds intrigue to the mystery. JWST's near-infrared spectrograph observed 3I Atlas on August 6, detecting not just the usual suspects like water ice and vapor, but also carbon dioxide and carbon monoxide in unusual proportions. The carbon dioxide to water ratio ranks among the highest ever measured in a comet at this heliocentric distance. This chemical signature suggests formation in the outer regions of its parent system. Beyond the carbon dioxide snowline, where temperatures drop below 125 degrees Celsius. Most solar system comets formed closer to their parent star, where water ice dominates over carbon dioxide ice. 3I Atlas carries the frozen memory of truly alien conditions. SphereX, the space-based infrared telescope, detected an extended carbon dioxide coma reaching hundreds of thousands of kilometers from the nucleus. That's a larger, more gas-rich envelope than casual observers might expect from telescope images. The visible light shows a relatively compact, bright region, but infrared reveals a massive invisible atmosphere surrounding the solid core. Here's where the physics gets uncomfortable. Even modest outflow rates should create detectable recoil. Gas escaping at hundreds of meters per second carries momentum. Conservation laws demand that momentum transfer to the parent body. A 1 kilometer's nucleus experiencing typical gas loss rates would show acceleration easily detectable by precision astrometry. Yet 4,022 positional measurements from 227 observatories show residuals consistent with pure gravitational motion. The observations span May 15th through September 23, 2025, more than 4 months of data covering the period when cometary activity was ramping up as 3I Atlas approached the inner solar system. The math is straightforward but striking. If you know the gas production rate and escape velocity, you can calculate expected recoil acceleration. If the observed acceleration falls below that prediction by a large margin, the object must be more massive than initial estimates suggested. It's detective work with momentum conservation as the primary witness. Current estimates suggest 3I Atlas loses roughly 150 kilos of mass per second through outgassing. That sounds modest, about the weight of 2 people every second. But over days and weeks, the cumulative momentum transfer should nudge even a substantial object into a measurably non-gravitational orbit. The fact that this nudge remains below detection limits implies extraordinary mass. Using typical comet densities around 500 kg per cubic meter, the 33 billion ton lower limit corresponds to a nucleus at least 5 kilometers in diameter. That's genuinely enormous by interstellar visitor standards. To put this in perspective, 1I Oumuamua probably measured less than 1 kilometer in its longest dimension and weighed perhaps millions of tons. 2I Borisov's nucleus spanned roughly 1 kilometer and contained billions of tons of material. 3I Atlas potentially outmasses both previous visitors by factors of 10 to 1,000, a genuine heavyweight in a field previously dominated by lightweights. The outflow velocity estimates around 404 km come from spectroscopic analysis of emission line profiles. When gas escapes from a comet nucleus, thermal motion and bulk flow combine to broaden spectral lines in characteristic ways. Modeling these line shapes provides velocity estimates, though the process involves assumptions about temperature distributions and gas dynamics. These velocities aren't unusual by comet standards. Solar system comets typically show gas escape speeds in the same range, driven by sublimation energy and the weak gravitational fields of small nuclei. What's unusual is the disconnect between substantial gas production and minimal orbital response. Visualization helps clarify the paradox. Imagine plotting comet mass versus non-gravitational acceleration for all known objects. Solar system comets cluster in a predictable relationship. Larger mass generally correlates with smaller acceleration for a given activity level. 1I Oumuamua sits off to one side, with high acceleration but no visible gas production. 2I Borisov falls neatly on the main trend line. 3I Atlas occupies empty space on this diagram, combining high mass with low acceleration in a way that stretches physical intuition. It behaves like a massive object that happens to sublimate ice, rather than an icy object that happens to be massive. The analogy writes itself. It looks like a comet, breathes like a comet, but shrugs off its own breath like a boulder. The disconnect between appearance and dynamics forces uncomfortable questions about what we're actually observing. Could the gas production estimates be wrong? Possibly, but JWST spectroscopy provides robust constraints on outflow rates. Could the acceleration measurements be systematically biased? Unlikely, given the global network of observatories and careful error analysis. Could the physics of momentum conservation be suspended? Definitely not. That leaves mass as the most plausible explanation. 3I Atlas appears to be genuinely anomalously massive, a quiet giant masquerading as an ordinary comet until precision measurements revealed its true nature. But who gathered the data precise enough to detect effects this small? Part 3. The Global Eye Network. The story of Three-Eye Atlas unfolds through the collective vision of hundreds of telescopes scattered across Earth's continents. When Avi Loeb, Andrea Gilbert, and Robert Warwick compiled their analysis, they drew from 4,022 individual measurements, contributed by 227 observatories, between May 15th and September 23, 2025. This represents one of the most comprehensive tracking campaigns ever mounted for an interstellar visitor. Astrometry, the precise measurement of celestial positions, forms the backbone of orbital mechanics. Every telescope that points at Three-Eye Atlas records its position in right ascension and declination coordinates, essentially celestial longitude and latitude. These measurements, accurate to fractions of an arc-second, accumulate into a detailed map of the object's motion against the starfield backdrop. Think of it as cosmic detective work. Each positional measurement represents a single snapshot, like a frame in a long exposure photograph of orbital motion. String enough frames together, and patterns emerge. Deviations from pure gravitational trajectories become visible as systematic residuals, the difference between where the object actually appears and where gravity alone would place it. The precision required to detect Three-Eye Atlas's non-gravitational acceleration limit staggers the imagination. We're talking about positional shifts smaller than 1 to 28,000 of an arc-second. To put that in perspective, it's like detecting the width of a human hair viewed from 20 kilometers away. Yet ground-based telescopes routinely achieve this precision through careful calibration and statistical analysis of multiple measurements. How does this translate to physical acceleration limits? The relationship involves orbital mechanics and geometry, but the basic physics is straightforward. Small accelerations accumulate over time as position shifts that grow quadratically, proportional to 1/2 x acceleration x time 2. After months of observation, even tiny non-gravitational forces should produce measurable orbital deviations. The upper limit of 15 mem/day2 emerges from this analysis. It sounds awkward in those units, but convert to more familiar terms, and you get roughly 10^9 mem/s2. That's extraordinarily small, about 1 in 10 millionth the acceleration you'd feel in a gently moving elevator. This level of precision requires a detective story approach, stitching thousands of pinpricks of light into a trajectory tight enough to test fundamental physics. Each observatory contributes its expertise and geographical perspective. Northern Hemisphere sites track Three-Eye Atlas during summer months, while southern observatories take over as Earth's rotation brings different sky regions into view. The discovery timeline reads like a modern astronomical thriller. Atlas Chile first spotted the object on July 1, 2025, initially catalogued as a potential asteroid. Recovery images, archival photos taken before official discovery, helped refine the orbital solution and establish the trajectory's interstellar nature. Within weeks, the Minor Planets Center reclassified it as humanity's third confirmed interstellar visitor. The Vera C. Rubin Observatory, still in commissioning phase, contributed early images that helped characterize both activity levels and precise astrometry. These observations preview the survey era dawning in astronomy, where massive telescopes will scan the entire southern sky every few nights, potentially discovering dozens of interstellar objects annually. Three-Eye Atlas represents a prototype for this coming revolution in transient discovery. Sub-arc-second precision buys astronomical investigators the ability to rule out non-gravitational pushes that would be obvious in smaller, less precisely tracked comets. When you can measure positions to milliarc-second accuracy and track objects for months, even subtle deviations from Newtonian mechanics become detectable. This precision transforms asteroids and comets from fuzzy dots into precisely mapped trajectories. Amateur astronomers and professional amateur collaborations fed early morphology and photometry time series into the global database. These observations, while perhaps less precise individually than major observatory measurements, provide crucial temporal coverage and help characterize how the object's brightness and appearance evolved as it warmed approaching the sun. The global coordination required for this kind of campaign showcases modern astronomy at its collaborative best. Observatories across time zones maintain continuous coverage as Earth's rotation carries each site into darkness. Radio networks coordinate pointing schedules. Data flows to the Minor Planet Center, where orbital analysts compile measurements into increasingly refined trajectory solutions. What makes this particularly impressive is the speed of the process. Unlike historical astronomical discoveries that might take months or years to confirm, 3I Atlas went from initial detection to detailed orbital characterization within weeks. Modern computing power, automated detection algorithms, and rapid communication networks compress discovery timelines that once stretched across seasons. The measurement precision achieved by this global network explains how researchers could place such tight constraints on non-gravitational acceleration. When you have thousands of positions measured to milliarc-second accuracy over months of observation, systematic deviations from gravitational trajectories become statistically significant, even if they're physically tiny. But precision comes with caveats that careful scientists always mention. These are positional residual limits, constraints on how much the observed trajectory differs from pure gravitational motion. They don't independently determine mass. Instead, they bound the acceleration parameter, which, when combined with gas flow models, yields the controversial mass estimates. The relationship between observed acceleration limits and inferred mass depends on assumptions about gas production rates, escape velocities, and momentum transfer efficiency. Change those assumptions, and the mass estimates change accordingly. The Global Telescope Network provides extraordinarily precise position measurements, but translating those into physical properties requires theoretical modeling. Still, the achievement deserves recognition. Detecting acceleration limits this small pushes ground-based astrometry to its practical limits. The Global Observatory Network essentially transformed Earth into a single planet-sized telescope with baseline separations spanning continents. Each observatory contributes its unique perspective and measurement capabilities to a collective endeavor that exceeds what any single facility could accomplish. The data quality enables tests of physics that were impossible just decades ago. When positional measurements become precise enough to detect 10^9 μm(s)2 acceleration, comets and asteroids transform from simple gravitational test masses into laboratories for studying momentum conservation, outgassing dynamics, and the subtle interplay between thermal physics and orbital mechanics. This level of observational sophistication explains how researchers could make such strong claims about 3I Atlas's anomalous nature. The measurements constraining its non-gravitational acceleration rank among the most precise ever achieved for any solar system object, interstellar or otherwise. When data quality reaches this level, unexpected results demand serious theoretical attention. The Global Eye Network watching 3I Atlas represents a preview of astronomy's future. Coordinated surveys, rapid response capabilities, and precision astrometry will become routine tools for studying not just interstellar visitors, but near-Earth objects, potentially hazardous asteroids, and the dynamical evolution of the solar system itself. But the images this network captured revealed something even more puzzling than a missing orbital push, a tail that seemed to point the wrong way. Part 4. The Coma Paradox. Hubble's July 21st image stopped astronomers in their tracks. Instead of the classic comet appearance, a bright nucleus trailed by dust streaming away from the sun, 3I Atlas displayed what observers described as a teardrop-shaped cocoon with a pronounced sunward glow. The forward-pointing anti-tail challenged basic intuitions about how comet debris should behave in interplanetary space. Most comet tails point away from the sun, swept outward by solar wind pressure and photon radiation. It's one of astronomy's most reliable visual cues, so reliable that ancient Chinese astronomers used comet orientations as celestial compasses. When you see a tail pointing toward our star, your brain starts working overtime trying to reconcile the image with basic physics. Anti-tails aren't completely unprecedented in solar system comets. They can result from viewing geometry, when Earth's orbital position creates an illusion of sunward-pointing material, or from unusual dust-grain dynamics, where larger particles follow ballistic trajectories different from fine dust swept by radiation pressure. But the persistence and prominence of 3I Atlas's forward glow made it notably unusual. Recent modeling papers explain the phenomenon through sublimating grain physics and perspective effects. As ice-rich particles escape the nucleus, they continue sublimating while traveling outward. Under certain conditions, this process can create apparent sunward features when viewed from specific angles. The mathematics work out, but the visual impact remains startling to observers accustomed to conventional comet morphology. 3I. Atlas's sunward glow persisted through July and August 2025 as telescopes tracked its evolution. This wasn't a brief geometric illusion that disappeared when viewing conditions changed. The forward-directed feature remained prominent in multiple observations from different observatories, suggesting real physical processes rather than simple perspective effects. Gemini South's August 27th observations revealed additional complexity as a more traditional anti-solar tail began emerging. The morphology was evolving in real time as the object warmed approaching perihelion. Early images showed primarily forward scattering, while later observations developed the classic dual-tail structure, with material streaming both toward and away from the sun. This evolving appearance matters because dust-to-gas ratios, grain lifetimes, and jet collimation patterns all affect how bright the comet appears and where its photocentric center, the brightness-weighted average position, falls relative to the actual nucleus. Since astrometric measurements track this photocenter, systematic changes in coma structure could potentially bias the orbital solutions used to infer non-gravitational acceleration limits. The challenge lies in separating genuine orbital dynamics from photocentric artifacts. If 3I Atlas's unusual morphology systematically shifts the apparent position of its brightness center, that could mimic or mask real non-gravitational forces. Careful analysis must account for these effects to avoid drawing incorrect conclusions about the object's mass and dynamics. Anti-tails in solar system comets typically result from well-understood physical processes, but the early prominence and persistence of 3I Atlas's sunward glow pushes into less familiar territory. The modeling community is actively working to understand whether standard dust dynamics and viewing geometry can fully explain the observations or whether more exotic processes might be involved. The chemistry overlays add another layer of complexity to the morphological puzzle. JWST detected carbon dioxide-rich outgassing, while Very Large Telescope spectroscopy revealed cyanogen and nickel emission lines without corresponding iron features. This combination, enhanced carbon dioxide, nickel without iron, and unusual dust morphology, paints a chemical portrait that doesn't match typical solar system comet templates. Nickel emissions aren't unprecedented in comets, but seeing nickel lines without accompanying iron signals raises questions about the underlying physics, potentially hinting at unique formation conditions or compositional anomalies in this interstellar wanderer. In most astronomical contexts, these metals appear together because they form from similar nucleosynthetic processes and often exist in similar chemical environments. The selective appearance of nickel suggests either unusual formation conditions or exotic release mechanisms. These chemical anomalies might connect to the morphological oddities through dust grain composition and sublimation dynamics. If 3I Atlas contains unusual metal-bearing minerals or organic compounds, their differential sublimation could create dust populations with different optical properties and dynamical behavior than typical comet debris. Visual explanations help clarify the anti-tail phenomenon for general audiences. Imagine animated vectors showing the sun's direction versus tail orientation, with perspective effects demonstrating how viewing angle can flip apparent relationships between the source and debris trail. When you're watching a three-dimensional process from a fixed vantage point, geometry can create optical illusions that challenge physical intuition. The sunward glow might result from forward scattering by dust grains with specific size distributions and compositions. When particles scatter sunlight preferentially in the forward direction, toward the observer rather than away from the sun, they can create brightness enhancements that appear to violate basic comet physics. The effect is real, but the interpretation requires careful consideration of scattering theory and particle properties. Still, caution is warranted when interpreting these morphological features. Anti-tails have appeared in solar system comets for decades without revolutionizing our understanding of dust dynamics. The prominence and persistence in 3I Atlas might indicate stronger activity levels or unusual dust properties rather than fundamentally new physics. The dust-to-gas balance affects not just visual appearance, but also the momentum transfer calculations central to mass estimates. If 3I Atlas produces more dust relative to gas than typical comets, or if its dust grains have different size distributions or compositions, that could alter the relationship between visible activity and expected non-gravitational acceleration. Understanding this balance requires combining observations across multiple wavelengths and techniques. Visible light images reveal dust scattering and morphology. Infrared spectroscopy maps, gas emissions and thermal properties. Radio observations can sometimes detect molecular transitions that trace gas production rates directly. Synthesizing these diverse datasets into coherent physical models challenges observational astronomers and theorists alike. The morphological evolution documented by Hubble, Gemini, and other facilities provides time series data crucial for testing dynamical models. As 3I Atlas warmed while approaching the Sun, different volatile species began sublimating at different rates. Water ice becomes active around 3 astronomical units from the Sun, carbon dioxide at much greater distances, and exotic species at their own characteristic temperatures. This chemical evolution should correlate with morphological changes as different gas species drive different dust entrainment processes. The fact that 3I Atlas's appearance continued evolving through the observation period suggests active sublimation processes responding to changing thermal conditions as orbital geometry brought it closer to solar heating. The visual metaphor that captures the essence of this puzzle. It looks like it's snowing toward the sun. Your brain rebels against the image because it violates everyday experience with how debris should flow in response to external forces. When comet tails point sunward, They're challenging fundamental assumptions about how matter behaves in the space environment. The Coma paradox exemplifies how 3I Atlas seems determined to violate expectations at every level, from its anomalous mass to its peculiar chemistry to its backward-looking tail. Each new observation adds complexity rather than clarity to the emerging picture of this interstellar visitor. But if 3I Atlas really is as massive as preliminary estimates suggest, that raises perhaps the most uncomfortable question of all. Where are all the smaller interstellar objects we should have discovered first? Part 5. The uncomfortable implication. The population statistics create a genuine puzzle that keeps astronomers awake at night. If 3I Atlas truly weighs 33 billion tons or more, with a nucleus spanning 5 kilometers or larger, it represents such an extreme outlier that basic assumptions about interstellar object demographics might need fundamental revision. We should have found dozens or hundreds of smaller visitors before encountering such a massive specimen. Think about it logically. Planetary systems eject debris through various mechanisms: gravitational scattering during planet formation, stellar flybys that perturb outer system objects, or instabilities in debris disks around young stars. In every plausible scenario, smaller objects get ejected more easily than larger ones. Less massive debris requires less energy to accelerate to escape velocity, making it inherently more numerous in the interstellar medium. Detection biases should further favor smaller objects, at least within certain size ranges. While the tiniest debris becomes invisible to current surveys, objects in the 100-meter to 1-kilometer range should be detectable when they pass through the inner solar system and develop visible coma. The fact that our first 3 interstellar visitors span such a dramatic mass range, from Oumuamua's millions of tons to 3I Atlas's potential tens of billions, defies naive statistical expectations. Observational selection effects provide one possible resolution. Wide-field surveys like ATLAS and the Catalina Sky Survey have only recently achieved the sensitivity and sky coverage needed to routinely detect interstellar visitors. The Vera C. Rubin Observatory, which will revolutionize transient astronomy, is just entering operations. We might be severely undersampling the actual population, seeing only the tip of a much larger iceberg. The detection order could reflect geometric coincidence rather than intrinsic rarity. 3I Atlas approached the inner solar system along a trajectory nearly aligned with the ecliptic plane, making it easier to spot and track than objects with highly inclined orbits. Its favorable geometry might have compensated for what would otherwise be a low detection probability for such rare, massive objects. Alternatively, the apparent anomaly might indicate that our understanding of ejection mechanisms is incomplete. Perhaps certain stellar environments preferentially eject larger objects, or maybe small interstellar debris gets destroyed more efficiently during the long journey between stars. Erosion by cosmic rays, collisions with interstellar dust, or sublimation driven by stellar encounters could preferentially remove smaller objects from the observable population. The fragility hypothesis deserves serious consideration. Objects with diameters less than a few hundred meters might not survive million-year journeys through interstellar space. If small debris gets sandblasted away by cosmic ray erosion or disrupted by thermal cycling around chance stellar encounters, the surviving population reaching our solar system could be biased toward larger, more robust specimens. But even accounting for these effects, 3I Atlas remains statistically uncomfortable. Population synthesis models that successfully explain asteroid belt demographics and Kuiper belt structure struggle to accommodate such massive interstellar visitors appearing so early in our discovery sequence. Either the models need updating, or Three-Eye Atlas represents a genuinely rare event that happened to occur during humanity's first serious survey for interstellar objects. The historical context adds perspective to this puzzle. Oumuamua's discovery in 2017 marked the beginning of serious interstellar object astronomy. 2I Borisov followed in 2019, establishing that some visitors behave like familiar solar system comets. 3I Atlas in 2025 completes a sample size of 3, statistically meaningless for drawing broad conclusions about population characteristics. We're essentially trying to understand the demographics of an entire galactic population based on 3 examples. It's like trying to characterize human height distribution after measuring only 3 randomly selected individuals. The sample size is so small that extreme outliers can completely distort statistical inference. Survey mathematics provides hope for resolving this uncertainty. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will scan the entire southern sky every few nights for 10 years, potentially discovering hundreds or thousands of interstellar objects. If 3I Atlas represents a typical visitor mass, Rubin should detect similar giants regularly. If it's a statistical fluke, the survey will flood discovery lists with smaller, more typical specimens. The stakes extend beyond academic curiosity about interstellar demographics. If massive objects like 3I Atlas are common, stellar system formation models need to explain how they get ejected efficiently. Current theories focus primarily on planetary migration and gravitational scattering during the early chaotic phases of system evolution. But these processes typically favor smaller debris ejection. Conversely, if 3I Atlas proves to be genuinely anomalous, its unusual properties might indicate exotic formation mechanisms or survival strategies that allowed it to reach unprecedented size before ejection. Understanding these processes could illuminate aspects of planetary system evolution that remain poorly understood even in our own solar neighborhood. The reservoir model problem cuts to the heart of galactic astrophysics. Stars form in clusters and associations where gravitational interactions between stellar systems can scatter debris across interstellar distances. The efficiency of these processes, combined with stellar formation rates over cosmic time, determines how many interstellar objects should be wandering through space at any given moment. Current estimates suggest the local interstellar medium contains billions of objects larger than 100 meter per PC3. Most of these remain invisible unless they pass close enough to the Sun to develop detectable coma or reflect sufficient sunlight for direct detection. The challenge lies in connecting theoretical population predictions with the small sample of objects actually observed. Ethical storytelling requires acknowledging what we don't know while maintaining scientific excitement about what we might discover. The 3I Atlas mass estimates could be wrong. The population statistics might reflect observational biases rather than genuine anomalies. The uncomfortable implications might dissolve as more data accumulates and theoretical models improve. But that uncertainty makes the story more compelling, not less. We're watching astronomy grapple with genuinely surprising observations that challenge established frameworks. Whether 3I Atlas proves typical or exceptional, it's forcing the field to confront fundamental questions about how matter moves between stellar systems and what that movement tells us about galactic evolution. The sample size problem will resolve itself as surveys improve and discovery rates increase. Within a decade, we'll have dozens or hundreds of interstellar visitors to analyze instead of just 3. Population statistics will transition from speculation to robust inference based on meaningful sample sizes. Until then, 3I Atlas stands as a puzzling ambassador from the space between stars, carrying information about conditions and processes in stellar environments we can barely imagine. Its anomalous properties, whether real or apparent, serve as prompts for better observations, improved models, and deeper questions about our place in the cosmic ecosystem. The uncomfortable implication remains. If we're finding massive interstellar objects before smaller ones, something important is missing from our understanding of how debris moves through the galaxy. The question is whether that something involves observational bias, theoretical gaps, or genuinely exotic physics operating in the vast spaces between stellar systems. But before we can resolve population statistics, we need to understand what current ejection and reservoir models actually predict about visitors like 3I Atlas. Part 6. The Interstellar Reservoir Problem. The galaxy operates like a vast redistribution network for planetary debris, with stellar systems continuously ejecting material that becomes the raw material for interstellar visitors. Understanding this cosmic recycling process requires modeling three primary ejection mechanisms: planet-planet gravitational scattering, close stellar flybys, and instabilities in protoplanetary disks around young stars. Planet-planet scattering dominates current theoretical frameworks. During the chaotic early phases of planetary system formation, massive bodies migrate through gravitational interactions that can fling smaller objects onto hyperbolic escape trajectories. This process resembles a cosmic billiard game where planets act as cue balls, striking asteroids and comets hard enough to launch them into interstellar space. The physics favors smaller projectiles. In this scenario, launch velocity scales inversely with object mass for a given gravitational encounter, meaning less massive debris achieves escape speed more easily than heavyweight specimens. A Jupiter-mass planet can easily eject kilometer-scale comets. But launching something the size of 3I Atlas requires much more specific geometric conditions and energy transfer. Stellar flybys provide an alternative ejection mechanism, particularly important in young stellar clusters where stars form in close proximity. When another star passes within a few hundred astronomical units of a planetary system, its gravitational influence can destabilize outer system objects and scatter them onto escape trajectories. The efficiency depends on flyby velocity, minimum approach distance, and the architecture of the target system's outer regions. These encounters can potentially eject larger objects than planet-planet scattering. Since stellar masses exceed planetary masses by factors of hundreds or thousands, a close flyby by a solar mass star could conceivably launch objects weighing billions or tens of billions of tons, making it a plausible mechanism for creating visitors like 3I Atlas. Disk instabilities during the earliest phases of system formation represent the third major ejection pathway. Before planets fully form, gravitational instabilities in massive protoplanetary disks can create spiral density waves and other non-axisymmetric structures that scatter embedded objects. This process operates during the first few million years of stellar evolution, when disks retain significant mass in gas and dust. The challenge lies in predicting which ejection mechanism dominates in different stellar environments and how the resulting size distribution compares with observations. Different stellar populations, young clusters versus field stars, metal-rich versus metal-poor systems, binary versus single-star environments, likely produce different ejection signatures and debris characteristics. Observational constraints remain frustratingly sparse given the small sample size of confirmed interstellar visitors. With only Oumuamua, 2I, Borisov, and 3I Atlas to analyze, uncertainties in population demographics span orders of magnitude. statistical inference becomes meaningless when outliers can completely dominate sample characteristics. The Vera C. Rubin Observatory's commissioning phase provided early glimpses of 3I Atlas that preview the coming revolution in interstellar object astronomy. Rubin's wide-field camera and rapid cadence survey will detect dozens or hundreds of such visitors annually, transforming population statistics from speculation into robust empirical science within the next decade. Current reservoir models attempt to connect ejection processes with observed visitor characteristics by modeling the buildup of interstellar debris over galactic timescales, star formation rates, stellar cluster dynamics, and planetary system architectures all contribute to determining how much material of various sizes should be wandering through local interstellar space. These models typically predict that smaller objects should vastly outnumber larger ones in the interstellar medium. The exact scaling depends on assumed ejection mechanisms and debris survival rates. But most frameworks suggest steep size distributions, where kilometer-scale objects are rare compared to 100 specimens. The disk lifetime problem adds urgency to theoretical modeling efforts. Protoplanetary disks around young stars typically dissipate within 5 to 10 million years due to photoevaporation by stellar radiation and accretion onto the central star. This limited time frame constrains how much material can be ejected during the disk phase versus later epochs, when planetary scattering dominates. If disk instabilities represent an important ejection mechanism for massive objects, the process must operate efficiently during these brief early phases. Objects like 3I Atlas would need to form and get ejected before their parent disks dissipate, imposing tight timing constraints on formation scenarios. Natural resolutions to the apparent population paradox include survivorship bias affecting different size ranges, detection geometry favoring certain object classes, or unusually dust-rich comae, making some visitors more detectable than their intrinsic brightness would suggest. Each possibility alters the relationship between observed and intrinsic population characteristics. Survivorship bias could operate through differential erosion rates during interstellar transit. Cosmic ray bombardment, sublimation driven by chance stellar encounters, or collisions with interstellar dust might preferentially destroy smaller objects over the million-year timescales required for travel between stellar systems. If only robust, massive specimens survive these hazards, the arriving population could be biased toward larger sizes. Detection geometry introduces another selection effect. Objects approaching the solar system near the ecliptic plane, like 3I Atlas, benefit from favorable observing conditions and extended visibility windows that simplify discovery and follow-up observations. Visitors with highly inclined or retrograde orbits might be systematically underrepresented in current detection statistics. Dust enhancement could make certain objects appear brighter than their nuclear size would predict, biasing discovery toward unusually active specimens, regardless of their intrinsic mass. If 3I Atlas produces more dust per unit nucleus area than typical comets, it might have been detectable at greater distances than similarly sized but less active visitors. The conservative scientific position treats the apparent anomaly as a prompt for better data rather than a definitive conclusion about population characteristics. 3 examples provide insufficient statistical power to constrain population models meaningfully. Extraordinary claims about demographic anomalies require extraordinary evidence, and current sample sizes fall short of that standard. Nevertheless, the theoretical challenge remains real. If subsequent surveys confirm that massive interstellar visitors appear more frequently than reservoir models predict, those models will need updating to accommodate either more efficient ejection of large objects or higher production rates in source stellar systems. The stakes extend beyond interstellar object demographics. Understanding ejection mechanisms and survival rates illuminates fundamental processes in planetary system formation and evolution. The debris wandering between stars carries information about conditions in stellar environments spanning the galaxy's history. Population synthesis efforts attempt to connect these diverse physical processes into coherent predictions about visitor characteristics by modeling stellar formation rates, cluster dynamics, planetary system architectures, and ejection efficiencies. Theorists can predict how many objects of various sizes should pass through the solar system per unit time. Current models span wide ranges in their predictions, reflecting uncertainties in underlying physical assumptions. Some frameworks predict interstellar object encounter rates on the order of 1 per year for objects larger than 100 minutes, while others suggest rates an order of magnitude higher or lower. 3I Atlas and its predecessors provide the first empirical constraints on these theoretical predictions. The reservoir problem ultimately connects local observations to galactic-scale processes operating over billions of years. Every interstellar visitor represents a sample from this vast population, carrying information about formation conditions, ejection mechanisms, and survival processes that operate in stellar environments we can never visit directly. As detection rates increase and sample sizes grow, population statistics will evolve from speculation to precision measurement. The apparent anomalies surrounding 3I Atlas might prove to be early data fluctuations, or they might indicate genuine surprises about how matter moves through the space between stars. But first, we need to understand the chemistry curveball that 3I Atlas threw at astronomers: nickel emissions without corresponding iron signals. Part 7. The Nickel Without Iron Mystery. Very Large Telescope, VLT spectroscopy, revealed something genuinely puzzling in 3I Atlas's coma. Multiple nickel emission lines blazing prominently in the infrared, while iron remained conspicuously absent from the same spectra. This chemical asymmetry challenges basic assumptions about metal emissions in cometary environments and adds another layer to the object's growing list of anomalous properties. The observation itself is straightforward but striking. VLT's high-resolution spectrographs detected several nickel atomic transitions in the 700 to 900 nanometer wavelength range during August 2025 observations. These lines appeared clearly above noise levels, with signal strength that allowed quantitative analysis of nickel production rates and spatial distribution within the coma. Iron lines, which astronomers expected to find at nearby wavelengths, simply weren't there. The spectra showed noise levels consistent with upper limits on iron emission that were significantly below typical detection thresholds for comets at similar distances from the Sun. This absence isn't just a failure to detect weak signals. It represents a genuine chemical peculiarity that demands explanation. Context makes the anomaly more significant. Nickel and iron often exist in similar chemical compounds in meteoritic and cometary materials. Seeing abundant nickel without corresponding iron is like finding a forest full of oak trees, but no maple trees in regions where both species normally coexist. The production rates derived from VLT spectroscopy show steep heliocentric distance scaling as 3I Atlas approached the Sun. Both nickel and cyanogen emissions increased dramatically with decreasing solar distance, following power law relationships with exponents around 8 to 9. This rapid brightening indicates strong temperature dependence in whatever process releases these species into the gas phase. Such steep scaling suggests the emission mechanism operates near a critical temperature threshold. As solar heating warms the nucleus surface, some process suddenly becomes efficient at liberating nickel atoms into the coma, where they can emit the observed spectral lines. The mathematics of this temperature dependence provides clues about underlying physical and chemical processes. Traditional comet chemistry offers several potential explanations for metallic emissions, though none perfectly matches the nickel without iron pattern observed in 3I Atlas. Direct sublimation of metal-rich minerals typically requires temperatures much higher than those achieved at the object's maximum solar distance during VLT observations. Something more subtle must be operating. Photodesorption represents one plausible mechanism. Solar ultraviolet radiation can break chemical bonds in surface materials, liberating atoms that would remain bound under purely thermal conditions. If 3I Atlas contains nickel-bearing compounds that are particularly susceptible to photodesorption, while iron-bearing phases remain more tightly bound, this could explain the observed chemical selectivity. Alternative hypotheses involve thermal lysis of organometallic compounds or metal-carbonyl complexes that might exist in the nucleus. These materials can decompose at relatively low temperatures, releasing metal atoms through chemical breakdown rather than direct sublimation of refractory minerals. If nickel forms more volatile compounds than iron in this interstellar environment, differential release could produce the observed abundance pattern. The cross-reference with JWST observations adds complexity to the chemical puzzle. JWST detected a carbon dioxide-rich coma with unusually high carbon dioxide to water ratios, painting a picture of formation in extremely cold conditions beyond the carbon dioxide snowline. Combined with prominent nickel emissions, this chemistry suggests formation environments quite different from typical solar system comet birth regions. These chemical signatures might indicate formation in the outer regions of stellar systems, where temperatures remain low enough for exotic ice phases and metal-rich compounds to condense. The interstellar journey would preserve these primordial compositions, allowing 3I Atlas to carry chemical fingerprints from alien stellar environments billions of years ago. What this chemistry does not prove deserves emphasis given media speculation. Some commentators noted that nickel without iron resembles certain industrial alloy compositions and suggested technological interpretations. This represents a logical leap unsupported by spectroscopic evidence. Metallic emissions in cometary comae come from well-understood atomic physics, not engineering processes. The media literacy aspect becomes important here. Second-tier websites and social media accounts amplified nickel equals artificial narratives that have no basis in peer-reviewed analysis. The VLT team presented their spectroscopic results as interesting examples of unusual but natural chemistry, not evidence for manufactured objects masquerading as comets. Distinguishing between genuine scientific anomalies and sensationalized misinterpretation challenges public understanding of how astronomy operates. Unusual chemistry deserves investigation and explanation, but unusual doesn't automatically imply artificial. The universe contains plenty of natural processes capable of producing unexpected elemental abundance patterns. Historical parallels exist in solar system comet research. Several comets have shown metal emissions with unusual abundance ratios that initially puzzled researchers before receiving natural explanations involving grain composition, temperature effects, or photochemical processing. The scientific method works by proposing hypotheses, testing predictions, and refining explanations as new data becomes available. The nickel emission lines themselves provide quantitative constraints on gas production rates and kinetic temperatures within the coma. Spectral line widths indicate thermal broadening and bulk motion velocities, while line intensity ratios constrain excitation conditions and density distributions. This information feeds into physical models of coma structure and evolution. Visual representation of the spectroscopic data helps clarify what VLT actually observed. Imagine a spectrum showing wavelength on the horizontal axis and brightness on the vertical axis. The nickel lines appear as distinct peaks at specific wavelengths, where atomic transitions emit characteristic photons. Iron lines should appear at different but predictable wavelengths, yet those spectral regions show only noise-level signals. The spatial distribution of nickel emissions within the coma provides additional clues about release mechanisms and transport processes. If nickel originates from discrete active regions on the nuclear surface, the emission should show corresponding spatial structure in high-resolution spectroscopic images. If it results from distributed grain processing, the distribution should appear more uniform. Current observations lack sufficient spatial resolution to map detailed coma structure, but future high-resolution spectroscopy could distinguish between localized and distributed emission scenarios. The extremely large telescopes coming online in the next decade will provide unprecedented spatial and spectral resolution for studying cometary chemistry. The temporal evolution of nickel emissions as 3I Atlas approaches perihelion will provide crucial tests of proposed release mechanisms. If photodesorption dominates, emission rates should correlate with solar flux intensity. If thermal processes control release, emissions should follow surface temperature evolution with appropriate time delays for thermal diffusion through surface layers. These observations represent more than just chemical curiosity. Metal emissions in cometary comae provide direct probes of refractory element abundances and chemical processing in environments that preserve primordial compositions from stellar system formation. Understanding these processes illuminates conditions in the early solar system and alien planetary environments. The nickel without iron mystery exemplifies how 3I Atlas continues violating expectations across multiple observational domains. From its anomalous mass to its peculiar morphology to its unusual chemistry, this interstellar visitor seems determined to challenge astronomical assumptions at every level of analysis. Such persistent anomalies historically drive scientific progress by forcing researchers to question fundamental assumptions and develop better theoretical frameworks. Whether 3I Atlas ultimately receives conventional explanations or reveals genuinely new physics, its unusual properties are already expanding our understanding of interstellar chemistry and comet evolution. Mysteries like this kept the Oumuamua debate alive for years, generating dozens of theoretical papers and observational follow-up campaigns. The scientific process thrives on such puzzles, using them as motivation for better instruments, more detailed observations, and more sophisticated theoretical models. But what happens when someone argues that the accumulating anomalies point toward a technological rather than natural explanation? Part 8. The Technological Hypothesis. The technological interpretation of 3I Atlas emerges from a convergence of unusual characteristics that, when viewed collectively, strain conventional explanations. Proponents point to statistical improbabilities in orbital geometry, the mass lower limit problem, precise planetary plane crossings, and the unusual chemical signatures as circumstantial evidence for artificial rather than natural origins. The ecliptic alignment provides the foundation for these arguments. 3I Atlas approaches the solar system with an orbital inclination of just 4.1 degrees relative to the planetary plane, a configuration that occurs randomly in only about one case out of 500 for objects arriving from arbitrary interstellar directions. While not impossible, such alignment raises eyebrows among researchers tracking visitor statistics. Harvard astronomer Avi Loeb has been among the most prominent advocates for taking technological possibilities seriously. though his presentations emphasize scientific methodology rather than definitive conclusions. His approach involves calculating probabilities for various natural scenarios and comparing them with alternative explanations that invoke artificial origins when conventional physics appears insufficient. The Jupiter intercept opportunity adds practical urgency to these theoretical discussions. Multiple papers by Loeb, Hibbs, and collaborators outline technically challenging but potentially feasible mission concepts for redirecting NASA's Juno spacecraft toward a close encounter with 3I Atlas during its March 16, 2026 passage near Jupiter. Such missions would require complex orbital mechanics involving third-body effect maneuvers near Jupiter to change Juno's trajectory toward an intercept course. The fuel requirements push against engineering limits, and success would depend on precise timing and execution. But the proposals demonstrate genuine scientific ambition to obtain close-up data rather than relying solely on remote observations. The mass estimates contribute to technological speculation through the elimination of conventional explanations. If 3I Atlas truly weighs tens of billions of tons with minimal non-gravitational acceleration, despite active outgassing, conventional comet physics struggles to accommodate such behavior. Technological advocates suggest that controlled propulsion could explain the disconnect between visible activity and missing orbital perturbations. Natural alternatives do exist for explaining the anomalous mass-to-acceleration ratio. Dust-driven forward scattering could create the observed sunward glow without requiring exotic physics. Carbon dioxide-rich ice chemistry might produce activity patterns that differ from typical water-dominated comets. Unusual grain size distributions or compositions could alter momentum transfer efficiency between escaping gas and solid nucleus. The burden of proof discussion becomes crucial when evaluating extraordinary claims. Absence of iron emissions or anomalously small accelerations might seem suggestive to some observers, but they do not constitute positive evidence for artificial propulsion. Extraordinary claims require extraordinary evidence. Resolved imagery showing manufactured structures, radar signatures inconsistent with natural materials, or unexpected trajectory changes beyond what outgassing physics predicts. Communication challenges arise when translating scientific uncertainty into public discourse. Headlines describing the perihelion passage on the far side of the Sun as intentional evasion misrepresent basic orbital mechanics. 3I Atlas follows a hyperbolic trajectory determined by its initial velocity vector and the solar system's gravitational field, not conscious navigation decisions. NASA and ESA maintain positions of treating 3I Atlas as natural unless compelling data suggests otherwise. This represents standard scientific conservatism, assuming conventional explanations until observations definitively rule them out. The space agencies continue monitoring the object with available assets while avoiding premature conclusions about its nature or origins. Testable predictions distinguish scientific speculation from unfounded conjecture. If 3I Atlas were indeed artificial, it might exhibit sudden post-perihelion trajectory changes beyond what outgassing physics predicts. Such deviations would appear as unexplained accelerations in continued astrometric monitoring by ground-based telescopes and space-based assets. Alternative observational signatures might include non-gray thermal emission patterns detectable by infrared space telescopes, coherent radio transmissions, or polarization characteristics inconsistent with natural dust scattering. Current observational capabilities make detecting such signatures challenging, but they represent concrete tests that could distinguish natural from artificial explanations. The detection geometry creates observational challenges that complicate hypothesis testing. 3I Atlas reaches perihelion on the far side of the Sun from Earth's perspective, creating a months-long observational blackout when the object disappears behind solar glare. This timing results from orbital mechanics rather than deliberate concealment, but it limits opportunities for continuous monitoring during the most dynamically active phase. The Parker Solar Probe's WHISPER, Wide Field Imager for Solar Probe, camera provides a unique vantage point coverage during the perihelion passage, potentially observing 3-eye atlas from solar perspectives unavailable to Earth-based telescopes. These observations could reveal activity patterns or morphological changes invisible from terrestrial viewpoints, contributing crucial data during the observational gap. The technological hypothesis serves important functions in scientific discourse, even if ultimately disproven. It provides alternative frameworks for interpreting unusual data, forces more rigorous analysis of conventional explanations, and motivates better observations to distinguish between competing models. Science benefits from intellectual diversity and skeptical examination of assumptions. However, maintaining appropriate skepticism requires distinguishing between legitimate scientific speculation and unfounded conspiracy theories. The technological interpretation of 3-eye atlas represents testable scientific hypothesis generation, not evidence-free assertion. Proponents present calculations, orbital analyses, and observational predictions that can be evaluated through standard scientific methods. The cultural context surrounding these discussions reflects broader societal fascination with potential evidence for extraterrestrial intelligence. Following decades of SETI searches and recent governmental acknowledgments of unidentified aerial phenomena, public interest in possible technological artifacts runs high. This enthusiasm can both motivate scientific investigation and distort interpretation of ambiguous data. Responsible science communication requires presenting multiple hypotheses while maintaining appropriate levels of confidence in different explanations. The technological interpretation deserves mention as one possibility among several, but current evidence remains insufficient to favor it over more conventional alternatives involving unusual but natural comet physics. The media amplification cycle demonstrates how scientific speculation can evolve into definitive claims through repeated reporting and social media sharing. Initial papers presenting technological possibilities as hypotheses requiring further investigation become transformed into assertions about probable artificial origins through successive retellings that lose important caveats and uncertainties. Educational opportunities arise from these discussions about hypothesis testing, statistical reasoning, and the scientific method. 3-eye atlas provides a real-time example of how scientists approach unusual observations, generate multiple explanations, design tests to distinguish between alternatives, and refine understanding as new data accumulates. The peer review process plays crucial roles in evaluating unconventional claims. While preliminary analyses and conference presentations can explore speculative ideas, definitive conclusions require rigorous evaluation by expert reviewers who examine methodology, statistical analysis, and interpretation of results. This quality control mechanism helps separate legitimate scientific inquiry from unfounded speculation. Future observations will provide decisive tests of the technological hypothesis through continued astrometric monitoring, spectroscopic analysis, and potential spacecraft encounters. If 3-eye atlas exhibits behavior consistent with natural comet physics, technological interpretations will fade. If observations reveal genuinely anomalous characteristics, the hypothesis gains credibility and motivates more detailed investigation. The timing of these definitive tests spans the next 18 months as 3-eye atlas completes its passage through the inner solar system and emerges from behind the Sun for continued Earth-based observations. This extended observational campaign provides multiple opportunities to test predictions from both natural and artificial origin scenarios. Regardless of ultimate conclusions, the technological hypothesis discussion highlights the importance of keeping open minds while maintaining rigorous standards for evidence evaluation. Science progresses through willingness to consider unconventional possibilities while demanding extraordinary proof for extraordinary claims. But there's another speculative framework that's equally fascinating and potentially more scientifically grounded: the possibility that objects like 3I Atlas serve as planet formation seeds. Part 9. The Planet Seeding Hypothesis. Suzanne Falsner's planet seeding hypothesis represents one of the most intriguing theoretical frameworks for understanding massive interstellar visitors like 3I Atlas. The concept suggests that interstellar objects captured by young stellar systems could bypass traditional planet formation bottlenecks and jumpstart giant planet growth during the brief window when protoplanetary disks retain sufficient mass to support rapid accretion. The traditional planet formation paradigm faces a significant timing problem. Giant planets must grow to substantial sizes before their parent protoplanetary disks dissipate through photoevaporation and stellar accretion. This process typically occurs within 5 to 10 million years of stellar birth, creating tight constraints on how quickly planetary cores can accumulate enough mass to trigger runaway gas accretion. Core accretion models struggle with what astronomers call the meter-size barrier: the tendency for growing planet embryos to spiral into their parent stars through aerodynamic drag before they can accumulate into larger, gravitationally bound objects. Small debris feels significant drag from disk gas, causing orbital decay that prevents growth to planet-size scales. Interstellar object capture offers an elegant solution to this timing problem. If young stellar systems can gravitationally capture pre-existing kilometer-scale objects from the interstellar medium, these ready-made seeds could bypass the slow growth phase and immediately begin accreting gas and dust from their host disks. The captured objects would already possess sufficient mass to resist aerodynamic drag while providing gravitational scaffolding for rapid planet assembly. Conference presentations at the 2025 European Planetary Science Congress and Division for Planetary Sciences meeting provided updated simulations supporting this capture scenario. New modeling indicates that massive stars capture interstellar objects more efficiently than lower-mass stellar systems, creating a potential correlation between stellar mass and giant planet occurrence that matches observational trends in exoplanet demographics. The mechanism works through gravitational focusing effects during close encounters between interstellar visitors and young stellar systems. More massive stars create deeper gravitational potential wells that increase capture cross-sections for passing objects. Additionally, massive stars often form in dense stellar clusters where encounter rates with interstellar debris remain high during the critical early phases of disk evolution. Recent press coverage has begun exploring how interstellar objects like 3I Atlas could theoretically bypass traditional planet formation barriers and accelerate growth processes. These explanations emphasize that capture seeding represents a complementary pathway rather than a replacement for conventional core accretion, potentially operating alongside traditional mechanisms in different stellar environments. The chemistry connection adds plausibility to seeding scenarios involving 3I Atlas. Specifically, JWST detected carbon dioxide-rich outgassing with abundance ratios suggesting formation far from the object's parent star, beyond the carbon dioxide snowline where temperatures remain below 25 degrees Celsius. Such frigid formation conditions would be typical for objects originating in stellar system peripheries. A captured interstellar visitor carrying foreign volatile compositions could introduce chemical diversity into its new host disk, potentially explaining some of the compositional variety observed in exoplanet atmospheres. Different stellar systems likely produce debris with different ice compositions and refractory element abundances, so capture processes would mix material from multiple stellar environments. Population statistics become crucial for evaluating the seeding hypothesis's viability. If the legacy survey of space and time discovers numerous interstellar visitors over the next decade, capture rates in young stellar systems become statistically plausible. If 3I Atlas proves exceptionally rare, seeding scenarios lose credibility due to insufficient raw material availability. Current theoretical work suggests that young stellar systems could capture interstellar objects at rates sufficient to influence planet formation outcomes. Dense star-forming regions provide both high encounter rates with passing debris and gravitational environments favorable for permanent capture. The process becomes most efficient during the first few million years, when stellar systems retain circumstellar disks massive enough to support rapid accretion onto captured seeds. Historical precedent for seeding concepts dates back several decades, but recent theoretical developments have provided more detailed predictions about capture rates, size distributions, and subsequent evolution. Prior work suggested that 10 million or more Oumuamua-scale seeds per protoplanetary disk could be present during peak formation epochs, representing a radical reframing of traditional planet formation paradigms. The capture efficiency depends on several factors, including relative velocity between interstellar visitors and target stellar systems, disk mass and structure, and the presence of binary companions or stellar cluster environments that modify gravitational dynamics. Different star formation environments likely produce different capture signatures and seeding efficiencies. Counter-arguments emphasize remaining uncertainties in capture mechanics, survival rates for captured objects, and migration processes that determine where seeds end up within their host disks. Capturing an object represents only the first step. The seed must survive tidal disruption, avoid ejection through subsequent gravitational encounters, and migrate to disk regions capable of supporting rapid accretion. Disk structure evolution adds complexity to seeding scenarios. Young protoplanetary disks experience rapid changes in density profiles, temperature distributions, and turbulent mixing that could either enhance or inhibit seed survival and growth. Understanding these processes requires sophisticated magnetohydrodynamic simulations that couple disk evolution with planetary formation physics. The observational signatures of seeding processes remain largely theoretical at present. Successful planet formation around captured interstellar seeds might produce chemical or isotopic anomalies detectable in mature planetary atmospheres. But such signatures would be extremely challenging to identify with current observational capabilities. Exoplanet demographics provide indirect tests of seeding hypothesis predictions. If capture processes significantly influence planet formation outcomes, they should leave statistical fingerprints in the mass distributions, orbital characteristics, and host star correlations observed in large exoplanet surveys. Some of these patterns might already be present in existing data sets. The theoretical framework requires careful distinction between what current models can predict reliably versus speculative extrapolations that require future observational testing. Capture cross-sections and gravitational focusing effects operate through well-understood physics, but subsequent evolution involves complex disk chemistry and dynamics that remain poorly constrained by observations. Visual representations of the seeding process help clarify the proposed mechanism. Imagine animations showing interstellar objects plunging into protoplanetary disks, experiencing drag forces that circularize their orbits and beginning to accrete surrounding gas and dust. The physics resembles conventional core accretion, but with a crucial head start provided by pre-existing solid cores. The timescale advantages become apparent when comparing seeding scenarios with traditional planet formation. Conventional core accretion requires several million years to build kilometer-scale planet embryos from dust grains, followed by additional time to grow to planet mass scales. Captured seeds begin this process with kilometer-scale masses already in place, potentially reducing total formation times by significant margins. Future theoretical work will refine capture rate predictions and evaluate survival probabilities under realistic disk evolution scenarios. These calculations require combining stellar cluster dynamics, interstellar object population models, and detailed protoplanetary disk physics, a challenging multiscale problem that pushes current computational capabilities. The connection between 3I Atlas and planet seeding remains speculative given current observational constraints. But the object's anomalous properties make it an interesting test case for evaluating whether massive interstellar visitors could plausibly serve as planet formation catalysts. If such objects prove common, seeding scenarios gain credibility. If they remain rare, conventional planet formation mechanisms continue dominating theoretical frameworks. The broader implications extend beyond individual objects to questions about how matter exchange between stellar systems influences galactic-scale evolution. If seeding processes operate efficiently, they represent a previously unrecognized pathway for chemical and physical communication between stellar environments separated by vast interstellar distances. This cosmic perspective raises fundamental questions about the uniqueness of individual planetary systems versus shared evolutionary processes operating across galactic scales. Understanding these connections requires bridging observational astronomy, theoretical astrophysics, and planetary science in ways that challenge traditional disciplinary boundaries. But regardless of the frameworks, the timing of these discoveries raises its own puzzles about why we're finding such massive interstellar objects. Part 10. The Cosmic Timing Puzzle. The confluence of technological capability, observational geometry, and cosmic coincidence that enabled 3I Atlas's discovery and detailed characterization represents a remarkable intersection of multiple converging factors. Understanding why we're detecting such massive interstellar visitors now requires examining the observational revolution transforming astronomy, the specific geometric advantages that made this object detectable, and the broader question of whether we're witnessing statistical fluctuations or genuine physical phenomena. The observational infrastructure supporting 3I Atlas's discovery has reached unprecedented sophistication within just the past few years. Atlas South began operations in 2022, providing Southern Hemisphere sky coverage that complements the original Hawaiian installations. This global network enables continuous monitoring of transient phenomena as Earth's rotation carries different observatory sites into optimal viewing conditions. Rapid response pipelines connecting Discovery telescopes with follow-up assets have compressed reaction times from weeks to hours. When Atlas Chile detected 3I Atlas on July 1, 2025, the Minor Planet Center classified it as potentially interesting within days. Hubble Space Telescope observations followed within 3 weeks, and JWST spectroscopy occurred just over a month after discovery. This coordination represents a quantum leap in astronomical responsiveness. The geometric factors favoring 3I Atlas's detection deserve emphasis because they might bias our perception of typical interstellar visitor characteristics. The object approached along a trajectory nearly aligned with the ecliptic plane, making it accessible to the majority of solar system survey telescopes that focus their efforts on regions where most asteroids and comets reside. This favorable geometry simplified follow-up observations by keeping 3i Atlas within the operational parameters of multiple observational facilities. Objects with highly inclined orbits or retrograde motion patterns would be systematically more difficult to discover and characterize, potentially biasing our sample toward ecliptic-aligned visitors like 3i Atlas. The media amplification cycle demonstrates how anomalously massive framing can attract attention while potentially overconfident interpretations of preliminary results. Initial mass estimates based on non-gravitational acceleration limits generated widespread interest, but these calculations rely on assumptions about outgassing physics that will be refined as peer review processes evaluate the underlying analysis. Viewer discretion becomes important when consuming news coverage about ongoing scientific investigations. The mass estimates, chemical anomalies, and population statistics surrounding 3i Atlas represent active areas of research rather than settled conclusions. Responsible science communication should distinguish between preliminary findings and established results while maintaining appropriate excitement about genuinely interesting discoveries. The spacecraft vantage point opportunities add unique perspectives unavailable from terrestrial observatories. The Parker Solar Probe's WHISPER camera will likely observe 3i Atlas during its late September to early November 2025 perihelion passage, providing solar-side coverage when Earth-based telescopes cannot observe the object due to its proximity to the Sun in the sky. These space-based observations could reveal activity patterns or morphological changes invisible from Earth's perspective. The different viewing geometry might resolve questions about the unusual sunward glow and evolving tail structure that have puzzled ground-based observers. Understanding 3i Atlas's behavior near perihelion requires data from multiple vantage points. Sample size effects provide the most straightforward explanation for apparent statistical anomalies in interstellar visitor characteristics. With only 3 confirmed examples, Oumuamua, 2i Borisov, and 3i Atlas, drawing conclusions about population demographics approaches meaninglessness. Early data fluctuations commonly produce misleading impressions that resolve as sample sizes increase. The alternative interpretation suggests that 3i Atlas genuinely occupies a rare tail of the interstellar object size distribution, representing a statistical unicorn that happened to appear during humanity's first systematic surveys. While improbable, such events occur by definition in the extreme tails of any distribution, and their rarity makes them memorable when they do appear. Hardware improvements across multiple observational domains have enhanced sensitivity to faint, distant objects while improving astrometric precision for tracking their motions. Ground-based adaptive optics systems reduce atmospheric blurring. Space-based telescopes eliminate atmospheric absorption, and improved detector technologies increase quantum efficiency and reduce noise levels. These technological advances shift the boundaries of detectability, potentially revealing objects that remained invisible to previous generation surveys. What appears to be a sudden appearance of massive interstellar visitors might actually reflect improved ability to detect objects that were always present, but previously beyond observational reach. Survey strategy evolution has optimized discovery rates through better cadence patterns, improved data processing algorithms, and enhanced coordination between complementary facilities. Modern surveys balance sky coverage with repeat observation frequency to maximize detection rates for different categories of transient phenomena, including interstellar visitors. The Vera C. Rubin Observatory represents the culmination of these technological and strategic improvements. When fully operational, LSST will scan the entire southern sky every few nights for 10 years, potentially detecting hundreds or thousands of interstellar objects and transforming population statistics from speculation into robust empirical science. Practical implications of the timing puzzle extend beyond academic curiosity to preparation for future discoveries. If massive interstellar visitors prove common, space agencies and scientific institutions need appropriate protocols for rapid response observations and potential mission planning. The infrastructure supporting 3I Atlas's characterization provides templates for future campaigns. The next 12 to 18 months represent the most data-rich observation window ever available for an interstellar visitor. Multiple space-based and ground-based facilities will track 3I Atlas through its complete passage around the Sun, providing unprecedented temporal coverage of activity, evolution, and chemical changes as the object responds to varying solar heating. Communication strategies for handling ongoing observations require balancing scientific uncertainty with public interest in potentially extraordinary discoveries. The scientific process operates through hypothesis generation, testing, and refinement over timescales that may not match media attention cycles or public expectations for definitive answers. Quality control mechanisms, including peer review, replication studies, and independent analysis, help distinguish genuine discoveries from instrumental artifacts or analysis errors. The initial mass estimates for 3I Atlas will undergo rigorous evaluation as the astronomical community examines methodology, assumptions, and alternative interpretations. Historical context provides perspective on how astronomical anomalies typically resolve through improved observations and theoretical understanding. Many objects initially classified as unusual or unprecedented eventually receive conventional explanations as data quality improves and models become more sophisticated. The scientific process self-corrects through this iterative refinement. The detection timing might simply reflect the natural progression of astronomical capability reaching thresholds necessary for systematic interstellar object discovery and characterization. Previous generations of surveys lacked the sensitivity, sky coverage, and follow-up capabilities required to detect and study visitors like 3I Atlas effectively. Educational value emerges from watching scientific methodology operate in real time on genuinely puzzling observations. 3I Atlas provides case study material for understanding hypothesis testing, statistical analysis, observational bias recognition, and the gradual accumulation of evidence that drives scientific progress. The broader cosmic perspective suggests that interstellar visitors carry information about galactic-scale processes operating over billions of years. Whether 3I Atlas proves typical or exceptional, it represents a sample from the vast population of debris wandering between stellar systems, offering glimpses into environments and processes we cannot study directly. Future survey capabilities will resolve timing puzzle questions through statistical analysis of large samples rather than speculation based on individual objects. The transition from anecdotal examples to population studies will occur within the current decade as next-generation facilities come online and detection rates increase dramatically. The apparent timing coincidence between technological readiness and massive visitor discovery might prove illusory as more objects populate our statistical samples. Alternatively, it might indicate that we've crossed observational thresholds that reveal previously hidden aspects of the interstellar medium and its debris content. Either way, 3i Atlas opens a crucial observational window that will define interstellar object astronomy for years to come. The techniques, protocols, and scientific questions emerging from its study will shape how we approach future discoveries and interpret their implications for understanding our place in the galactic ecosystem. This brings us to perhaps the most exciting immediate prospect: the chance to observe 3i Atlas from an entirely different vantage point as it approaches Mars. Part 11. The Mars Encounter. The cosmic choreography bringing 3i Atlas within 30 million kilometers of Mars on October 3, 2025, creates an unprecedented opportunity for multi-vantage point observations of an interstellar visitor. This encounter distance of roughly 0.2 astronomical units places the object well within the operational range of Mars-orbiting spacecraft, potentially providing the first close-up views of an interstellar comet from assets positioned beyond Earth's immediate vicinity. European Space Agency missions currently operating around Mars include Mars Express, launched in 2003 and still functioning after more than 2 decades of service, and the Trace Gas Orbiter, which arrived in 2016 as part of the ExoMars program. Both spacecraft carry imaging systems and scientific instruments that could potentially observe 3i Atlas during its Mars passage, though operational constraints and power limitations require careful mission planning. NASA's MAVEN orbiter, studying Martian atmospheric escape processes since 2014, represents another potential observer during the encounter period. While primarily designed for atmospheric research rather than deep space observations, MAVEN's instruments might contribute to the observation campaign if mission managers can accommodate pointing requirements and data collection priorities. The Mars Reconnaissance Orbiter, operational since 2006 with its high-resolution imaging science experiment, HiRISE, faces significant challenges in observing 3i Atlas due to the enormous distance involved. Even at closest approach, the object remains tens of millions of kilometers from Mars, far beyond HiRISE's optimal resolution capabilities, which work best for surface features measured in meters rather than distant objects measured in kilometers. Nevertheless, any Mars-based observations would provide valuable constraints on brightness profiles, phase angle effects, and coma asymmetry that cannot be obtained from Earth-based telescopes during the same time period. The different viewing geometry offers perspectives on dust scattering and gas distribution patterns that might appear quite different when observed from Mars versus Earth orbital positions. The scientific value of Mars encounter observations extends beyond simple imaging to include photometric measurements that could constrain activity levels and help test the theoretical frameworks connecting visible outgassing with inferred mass estimates. Independent brightness measurements from a Mars orbital perspective would complement Earth-based observations and potentially resolve discrepancies in activity level assessments. Coordination between Mars assets and ground-based telescopes requires precise timing and communication protocols to ensure simultaneous observations where possible. The light travel time between Earth and Mars, approximately 16 minutes during the encounter period, complicates real-time coordination, but allows for planned observation sequences designed to maximize scientific return. Communication planning becomes crucial for transmitting observational data back to Earth within reasonable timeframes. Mars orbiter data rates vary depending on orbital geometry and Earth-Mars relative positions, but the encounter period offers favorable communication windows that should allow timely data return for integration with Earth-based observations. The encounter timeline spans several days around the October 3rd closest approach, providing multiple observation opportunities as 3i Atlas moves across Mars-centered sky backgrounds. Different spacecraft have different orbital periods and pointing capabilities, so observation windows vary among the available assets. Brightness predictions suggest that 3i Atlas should remain detectable by sensitive Mars orbiter instruments during the encounter period, though the exact visibility depends on coma development, dust production rates, and the object's intrinsic nuclear brightness. Models based on Earth-based observations provide planning estimates, but actual detectability will depend on the object's behavior as it continues warming while approaching the Sun. The geometric advantage of Mars-based observations becomes apparent when considering Earth's perspective during the same time period. From our planet, 3i Atlas appears increasingly close to the Sun in the sky as it approaches perihelion, creating challenging observing conditions due to solar glare and atmospheric scattering. Mars orbiters face no such atmospheric limitations and observe from a different geometric perspective. Safety considerations for Mars missions remain minimal given the encounter distances involved. 30 million kilometers represents roughly 75 times the distance between Earth and the Moon, close by astronomical standards, but presenting no collision risk or operational hazards to Mars orbiting spacecraft. The observation opportunity comes with essentially zero mission risk. Historical context provides perspective on previous Mars-based observations of solar system objects. Mars orbiters have occasionally observed asteroids, comets, and other solar system bodies when geometric conditions proved favorable. Though none of these previous observations involved interstellar visitors with the unusual characteristics attributed to 3i Atlas. The technical challenges include spacecraft pointing accuracy, instrument calibration for unexpected targets, and data processing pipelines designed for Mars surface and atmospheric observations rather than distant point sources. Mission teams must adapt existing operational procedures to accommodate targets quite different from their primary science objectives. Data integration between Mars-based and Earth-based observations will require standardized formats, cross-calibration of instruments, and collaborative analysis pipelines to merge datasets effectively, ensuring that the combined observations yield a comprehensive view of 3i Atlas's behavior during this rare multi-perspective window. Careful cross-calibration and geometric modeling are essential to ensure that measurements from different vantage points can be meaningfully compared. The different viewing angles, filter systems, and detector characteristics must be accounted for in any combined analysis. Scientific return expectations should remain realistic, given the technical limitations and distance constraints involved. Mars encounter observations will likely provide photometric data and possibly low-resolution morphological information, rather than detailed structural analysis of the nucleus or coma. Even limited data would represent valuable additions to the observational data set. The observation campaign represents a preview of future multi-asset coordination for studying transient phenomena throughout the solar system. As interplanetary missions become more numerous and capabilities improve, coordinated observations from multiple vantage points will become routine tools for studying asteroids, comets, and other visiting objects. Communication with the public about Mars encounter observations requires managing expectations while maintaining enthusiasm for the scientific opportunities. The distances involved preclude high-resolution imagery of the type that captures the popular imagination, but the scientific value of multi-vantage point photometry and astrometry deserves appreciation. The Mars encounter also provides a natural transition toward even more exciting observation opportunities as 3i Atlas continues its journey through the inner solar system. The October observations from a Mars orbital perspective represent just the beginning of an extended observation campaign that will culminate in close approaches to other planetary systems. Mission planning for Mars encounter observations must balance scientific opportunity with operational constraints, including spacecraft health, power availability, communication schedules, and primary mission priorities. The European and American space agencies will make decisions about observation participation based on technical feasibility and resource allocation considerations. Regardless of specific participation by individual Mars missions, the encounter represents a unique moment in interstellar object astronomy when multiple assets across the solar system could simultaneously observe the same visitor from different perspectives. Such opportunities are rare and valuable for advancing understanding of these mysterious travelers from interstellar space. The data collected during the Mars encounter, combined with continuous Earth-based monitoring, will provide unprecedented temporal and geometric coverage of an interstellar object's evolution as it responds to changing solar heating conditions while approaching perihelion. This comprehensive observation campaign continues building toward an even more spectacular opportunity as 3I Atlas approaches its next major gravitational encounter near Jupiter. Part 12. The Jupiter Opportunity, the gravitational dance bringing 3I Atlas within 53.6 million kilometers of Jupiter on March 16, 2026, represents perhaps the most scientifically valuable observation opportunity in the object's entire passage through our solar system. At 0.358 astronomical units from the gas giant, this encounter distance places the interstellar visitor within potential range of NASA's Juno spacecraft, currently conducting extended mission operations in Jovian orbit. Multiple research papers have outlined ambitious mission concepts for redirecting Juno toward an intercept trajectory with 3I Atlas, using gravitational assist maneuvers and the spacecraft's remaining fuel reserves. These proposals, developed by teams including Loeb, Hibbs, Cragg, and other researchers, represent technically challenging but potentially feasible engineering solutions for achieving humanity's first close encounter with an interstellar visitor. The orbital mechanics involved in such a rendezvous mission would require what aerospace engineers call an Oberth effect maneuver, using Jupiter's gravitational field to amplify the effectiveness of Juno's propulsive burns. By firing the spacecraft's engines at the point of closest approach to Jupiter, where orbital velocities reach their maximum, each unit of propellant provides maximum momentum change for trajectory modification. Congressional interest in the mission concept reached official levels when representatives sent a letter to NASA urging detailed study of repurposing Juno for interstellar object investigation. This political attention underscores the extraordinary public fascination surrounding 3I Atlas and reflects growing recognition that such opportunities may not arise again for decades or longer. The scientific payoff from successful in situ sampling would dwarf anything achievable through remote observations alone. Juno's instruments could potentially analyze dust composition directly, measure grain size distributions, determine isotopic ratios, and characterize magnetic properties, data quality levels that remain impossible using ground-based telescopes or even space-based observatories operating from Earth's vicinity. Direct sampling would provide definitive tests of the chemical anomalies inferred from spectroscopic observations. The nickel without iron puzzle, the carbon dioxide-rich ice composition, and other unusual characteristics could be verified or refuted through direct contact with the object's coma and debris trail. Such measurements would settle questions about 3I Atlas's nature that might otherwise remain unresolved for years. Risk-benefit analysis for the mission. Repurposing involves trading primary science objectives against once-in-a-lifetime opportunities for breakthrough discoveries. Juno's extended mission focuses on detailed mapping of Jupiter's gravitational field, magnetic environment, and atmospheric dynamics. Redirecting it toward 3I Atlas would necessarily curtail these investigations in favor of interstellar visitor science. The fuel limitations present the primary technical constraint on mission feasibility. Juno was not designed for major trajectory changes and carries limited propellant reserves for station keeping and orbital adjustments around Jupiter. Reaching 3I Atlas would require expenditure of essentially all remaining fuel, ending any possibility of returning to Jupiter science operations. Engineering assessments must evaluate whether Juno's propulsion system can deliver sufficient velocity change to achieve intercept trajectories within available fuel margins. The calculations involve complex orbital mechanics, accounting for Jupiter's gravitational field, the spacecraft's current trajectory, and the predicted path of 3I Atlas through the outer solar system. Alternative observation strategies using other assets might provide scientifically valuable data without requiring complete mission redirection. The European Space Agency's JUICE mission, currently en route to the Jovian system, might achieve distant observations depending on arrival timing and orbital geometry. NASA's Psyche spacecraft, traveling toward the asteroid belt, could potentially contribute depending on trajectory alignment. Ground-based telescopes will continue providing valuable observations throughout the Jupiter encounter period, offering complementary data to any spacecraft observations. The James Webb Space Telescope, Hubble Space Telescope, and large ground-based facilities will maintain monitoring campaigns regardless of spacecraft participation decisions. The Sphere-X Space Telescope, designed for all-sky infrared surveys, could contribute unique observations of 3I Atlas's extended carbon dioxide coma during the Jupiter encounter timeframe. Sphere-X's wide field coverage and infrared sensitivity make it well-suited for tracking large-scale coma evolution as the object continues warming while approaching perihelion. Policy implications of the mission concept extend beyond immediate scientific considerations to broader questions about planetary defense preparedness, interstellar visitor response protocols, and international coordination for studying potentially significant astronomical discoveries. The precedent established by 3I Atlas will likely influence future response strategies. Cost-benefit calculations must weigh the guaranteed loss of primary Juno mission science against the uncertain but potentially transformative gains from direct interstellar visitor investigation. Such decisions involve not only technical feasibility assessments, but also scientific priority judgments about the relative importance of different research objectives. The observation geometry during the Jupiter encounter offers advantages and disadvantages compared with other observation windows. The outer solar system location provides excellent viewing conditions free from solar interference, but the enormous distance from Earth complicates real-time communication and reduces apparent brightness for ground-based telescopes. Mission timeline constraints add urgency to decision-making processes. Spacecraft trajectory modifications require months of planning, analysis, and implementation. If NASA decides to attempt Juno redirection, the approval and execution process must begin well before the actual encounter opportunity to allow sufficient time for orbital adjustments. International cooperation possibilities include coordination with European and Japanese assets in the Jupiter system, sharing of observational data, and joint analysis of any samples or measurements obtained during encounter operations. The global interest in 3I Atlas makes international collaboration both scientifically valuable and politically advantageous. Public engagement opportunities surrounding the Jupiter encounter decision process provide educational moments for explaining how space agencies balance competing scientific priorities, evaluate technical risks, and make decisions about resource allocation under uncertainty. The visible decision-making process offers insights into how aerospace institutions operate. Historical precedent for mission repurposing includes several successful examples where spacecraft originally designed for one purpose were redirected toward unexpected opportunities. The deep impact flyby of Comet Hartley 2 and various asteroid belt encounters by missions originally targeted elsewhere demonstrate that flexible mission planning can yield exceptional scientific returns. The technical requirements for Juno redirection include precise navigation solutions, thermal management for extended cruise phases, instrument recalibration for different target characteristics, and communication protocol modifications to support operations at greater distances from Earth than originally planned. Scientific instrument capabilities aboard Juno include magnetometry, gravity field mapping, microwave radiometry, infrared imaging, and charged particle detection. Tools that could provide unique insights into 3I Atlas's physical properties, composition, and interaction with the solar wind environment. Data return expectations must account for communication limitations at Jupiter distances and the finite lifetime of spacecraft systems operating beyond their design specifications. Any Juno encounter with 3I Atlas would likely represent the spacecraft's final major scientific contribution before end of mission. The decision process timeline will unfold over the coming months as NASA evaluates the technical feasibility, scientific merit, and resource implications of potential mission redirection. Whatever the outcome, the Jupiter encounter opportunity has already demonstrated the extraordinary scientific interest generated by 3I Atlas and its anomalous characteristics. Whether through direct spacecraft encounter or continued remote observations, the Jupiter phase of 3I Atlas's journey will provide crucial tests of theoretical frameworks attempting to explain its unusual properties. But regardless of how the observational chips fall, theorists will need to respond to whatever data emerges from these unprecedented observation campaigns. Part 13. The Theoretical Fallout. The theoretical implications of 3I Atlas extend far beyond single-object characterization into fundamental questions about interstellar debris populations, planetary system formation mechanisms, and the chemical evolution of matter throughout galactic history. Whether the preliminary mass estimates prove accurate or require significant revision, the object has already forced astronomers to confront gaps in theoretical understanding that will drive research directions for years to come. If subsequent analysis confirms the 5-kilometer nucleus diameter and 33 billion ton mass estimates, interstellar object population models face serious challenges in explaining how such massive debris gets ejected from planetary systems and survives transport through interstellar space. Current ejection mechanisms struggle to launch objects this large efficiently, suggesting either that theoretical frameworks need updating or that 3I Atlas represents an extreme statistical outlier. The population statistics problem would demand new theoretical work on ejection processes, particularly mechanisms capable of launching massive objects without destroying them through tidal forces or collision cascades. Stellar flyby scenarios might need re-evaluation, while planet-planet scattering models would require examination of rare geometric configurations that could eject kilometer-scale objects without fragmentation. Alternatively, if future observations reduce the mass estimates to more conventional values, the lesson becomes one about how coma physics and outgassing dynamics can fool observers into inferring incorrect physical properties. Such an outcome would represent a significant advance in understanding non-gravitational forces and their relationship to observable comet characteristics. The theoretical framework connecting visible activity to inferred acceleration limits involves complex physics of momentum transfer between escaping gas and solid nucleus material. If 3i Atlas demonstrates that these relationships are more complicated than previously assumed, comet physics models across the board would need updating to account for previously unrecognized processes. Chemistry pathways for explaining the nickel without iron emission pattern will likely generate extensive theoretical investigation, regardless of the object's ultimate mass determination. The selective appearance of nickel lines without corresponding iron features challenges standard models of metal release mechanisms in cometary coma, suggesting either exotic chemical compounds or unusual physical processes. Photodesorption models, thermolysis scenarios involving organometallic complexes, and differential sublimation of metal-bearing phases all represent theoretical frameworks that could potentially explain the observed emission patterns. Testing these alternatives requires detailed laboratory experiments and sophisticated chemical modeling of low-temperature, low-pressure environments. The carbon dioxide-rich chemistry detected by JWST adds another theoretical challenge by indicating formation conditions quite different from typical solar system comet birth environments. Understanding how objects form with such unusual volatile compositions requires models of chemical evolution in the outer regions of stellar systems, where temperatures remain below -125 degrees Celsius. Morphological modeling efforts will focus on explaining the persistent sunward glow and evolving anti-tail structure through dust dynamics and viewing geometry effects. These theoretical investigations could advance general understanding of how dust grains behave in cometary comas, with applications extending beyond interstellar visitors to solar system comets exhibiting similar phenomena. The theoretical work will need to address why 3i Atlas shows such unusual morphology compared with previous interstellar visitors like 2i Borisov, which behaved like conventional solar system comets in most respects. Understanding these differences could illuminate the diversity of formation and evolution processes operating in different stellar environments. Population consequences of the 3i Atlas observations will drive theoretical work on interstellar object demographics and their implications for planetary system formation throughout the galaxy. If massive visitors prove common, theoretical frameworks for understanding debris ejection and transport between stellar systems will require fundamental revision. The Vera C. Rubin Observatory's impending flood of interstellar object discoveries will provide statistical constraints on population models within the next few years. Theoretical predictions about size distributions, chemical compositions, and orbital characteristics can be tested against large samples rather than speculative extrapolation from individual examples. Planet seeding hypothesis development will accelerate in response to 3i Atlas observations, particularly if the object's massive nature proves typical rather than exceptional. Theoretical work on capture cross-sections, survival rates, and subsequent evolution within protoplanetary disks will need to become more sophisticated to make testable predictions. The seeding scenarios require coupling stellar dynamics, disk evolution, and planetary formation physics in ways that challenge current computational capabilities. If interstellar visitors like 3i Atlas commonly get captured by young stellar systems, these processes could represent previously unrecognized pathways for rapid planet formation. Cultural implications of the 3i Atlas observations extend beyond technical astronomy into broader questions about how scientific communities respond to unusual data and evaluate extraordinary claims. The object has generated discussions about the boundary between legitimate scientific speculation and unfounded conjecture, which could influence future approaches to anomalous observations. The media coverage and public interest surrounding 3i Atlas demonstrate both the benefits and challenges of conducting cutting-edge research in the social media age. Theoretical work must now consider not only scientific accuracy, but also potential misinterpretation and sensationalization of preliminary results. Science communication strategies will need to evolve in response to the 3i Atlas experience, balancing legitimate scientific excitement about unusual discoveries with appropriate caution about preliminary findings that have not yet undergone rigorous peer review. The theoretical response to 3i Atlas will likely follow historical patterns where initial anomalous observations generate multiple competing explanations that gradually converge toward consensus as more data becomes available and theoretical frameworks mature. The process can take years or decades for genuinely challenging observations. Interdisciplinary collaboration between astronomy, planetary science, chemistry, and physics will become increasingly important as researchers attempt to explain 3i Atlas's diverse anomalous characteristics. No single theoretical framework seems capable of addressing all the unusual observations simultaneously. Laboratory experiments will play crucial roles in testing theoretical predictions about metal emission mechanisms, dust grain behavior, and chemical processes operating in low-temperature, low-pressure environments characteristic of cometary coma. These experimental programs could provide definitive tests of competing theoretical explanations. Computational modeling capabilities will need advancement to handle the complex multi-fluid physics problems posed by 3i Atlas observations. Coupling gas dynamics, dust transport, chemical reaction networks, and radiative transfer processes require sophisticated numerical codes that push current computational limits. The theoretical legacy of 3i Atlas will likely extend far beyond the object itself into general advances in comet physics, interstellar medium understanding, and planetary formation theory. Even if the object ultimately receives conventional explanations, the theoretical work it inspires will advance multiple fields simultaneously. Future theoretical predictions should be formulated as testable hypotheses that upcoming observations can evaluate objectively. The scientific value of 3i Atlas lies not only in its unusual characteristics, but also in its role as a catalyst for generating falsifiable theoretical frameworks that can be evaluated through observation. The theoretical fallout represents both challenge and opportunity for advancing fundamental understanding of how matter behaves and evolves throughout cosmic history. Whether 3i Atlas proves revolutionary or ultimately conventional, it has already succeeded in forcing astronomers to think more deeply about processes operating between stellar systems. This theoretical ferment provides the intellectual backdrop against which we must evaluate the various fringe interpretations and faithful adherence that 3i Atlas has attracted. Part 14. The Fringe and the Faithful. The media ecosystem surrounding 3i Atlas reveals the complex dynamics of how scientific uncertainty transforms into public narrative, with some outlets amplifying speculative technological interpretations while others push back with equal force. This polarization demonstrates the challenges of communicating genuinely anomalous observations in an era where scientific nuance often gets lost in the rush toward definitive explanations. Examination of coverage across different media platforms shows remarkable variation in how the same scientific data gets interpreted and presented. Some outlets emphasize the statistical improbabilities and unusual characteristics as potential evidence for artificial origins, while others stress the preliminary nature of mass estimates and the availability of natural explanations for most observed phenomena. The technological interpretation finds its most prominent advocate in Harvard astronomer Avi Loeb, whose actual statements often prove more nuanced than headline summaries suggest. Loeb typically frames artificial origins as possibilities requiring further investigation rather than established conclusions, emphasizing scientific methodology over definitive claims about 3i Atlas's nature. His approach involves calculating probabilities for various scenarios and comparing the likelihood of natural versus artificial explanations when conventional physics appears insufficient to explain observations. This represents legitimate scientific hypothesis generation, though the boundaries between speculation and evidence-based conclusion can become blurred in public discourse. Critics of the technological interpretation argue that extraordinary claims require extraordinary evidence and that current observations of 3I Atlas, while unusual, fall short of the definitive proof necessary to invoke artificial explanations. They emphasize that comet physics remains incompletely understood and that natural processes could potentially explain all observed anomalies. The orbital geometry issue exemplifies how scientific statistics can be interpreted in different ways depending on underlying assumptions. The 4.1-degree ecliptic inclination occurs randomly in roughly one case out of 500, which technological proponents cite as evidence against natural origins. Critics counter that selection effects in survey geometry might bias detection toward ecliptic-aligned objects. Perihelion timing provides another contentious issue where identical facts support different interpretations. The object reaches closest approach to the Sun on the far side from Earth's perspective, creating months of observational blackout due to solar glare. Some coverage describes this as intentional evasion, while others explain it as straightforward orbital mechanics. NASA's public position maintains scientific conservatism by treating 3I Atlas as natural unless compelling data suggests otherwise. This institutional stance reflects standard scientific methodology that assumes conventional explanations until observations definitively rule them out, avoiding premature conclusions about extraordinary claims. The ESA's geometric analysis explicitly addresses evasion narratives by explaining that 3I Atlas follows a hyperbolic trajectory determined by its initial velocity vector and gravitational physics, not conscious navigation decisions. Solar system geometry places perihelion on the Sun's far side relative to Earth, purely through mathematical coincidence. Responsible speculation segments in quality science coverage typically list potential smoking gun observations that would shift scientific consensus toward artificial interpretations. These might include sustained powered maneuvers beyond what outgassing physics predicts, coherent narrowband radio emissions, engineered reflectance patterns, or non-ballistic trajectory changes. Such criteria provide objective standards for evaluating technological claims that go beyond subjective interpretation of ambiguous data. The absence of these definitive signatures suggests that current observations, while interesting, remain insufficient to support extraordinary conclusions about 3I Atlas's origins. Debunking efforts appropriately remind audiences that comet tails and volatile spectra represent exactly what astronomers expect from natural comets, including interstellar ones. 2I Borisov demonstrated that interstellar comets can behave identically to solar system specimens, providing a baseline for normal behavior that 3I Atlas's anomalies can be compared against. The community dynamics surrounding 3I Atlas illustrate how modern scientific communication operates through interaction between peer-reviewed publications, conference presentations, preprint servers, social media platforms, and traditional press coverage. Each communication channel operates with different standards for evidence evaluation and fact-checking. Preprint servers like arXiv allow rapid dissemination of research results before peer review, enabling fast response to time-sensitive observations, but potentially amplifying preliminary findings that might not survive rigorous evaluation. The 3I Atlas mass estimates circulated through preprints before formal publication creating opportunities for both legitimate scientific discussion and premature conclusion drawing. Medium posts and personal blogs provide additional venues for scientific speculation that operate outside traditional peer review mechanisms. While these platforms enable creative hypothesis generation and public engagement with cutting-edge research, they also create pathways for unfounded speculation to gain apparent credibility through viral sharing. Press office coordination between universities and media outlets shapes how scientific discoveries get translated into public understanding. The 3i Atlas coverage demonstrates both successful examples of nuanced science communication and cautionary examples of how preliminary findings can be oversimplified or sensationalized. Social media amplification creates feedback loops where initial speculative coverage generates additional speculation that references itself, potentially creating false impressions of widespread scientific support for ideas that remain highly tentative. The viral nature of extraordinary claims can outpace more cautious scientific evaluation processes. Quality science journalism distinguishes between what researchers actually say and how their statements get interpreted or extrapolated by others. Careful reporting includes appropriate caveats about preliminary findings, acknowledges competing explanations for unusual observations, and provides context about typical scientific methodology for evaluating extraordinary claims. Educational opportunities emerge from examining how scientific speculation evolves into public understanding through various communication channels. 3i Atlas provides real-time examples of hypothesis generation, peer review processes, and the gradual accumulation of evidence that either supports or refutes initial theoretical proposals. The object also demonstrates how genuine scientific mysteries can attract both legitimate research interest and fringe speculation simultaneously. Distinguishing between rigorous scientific investigation and unfounded conjecture requires understanding how professional astronomy operates and what standards of evidence the field considers convincing. Public media literacy becomes crucial for navigating the complex landscape of scientific information, where legitimate uncertainty gets mixed with speculation, preliminary findings get presented as established facts, and extraordinary claims compete for attention with more mundane but better supported explanations. Viewer engagement strategies should encourage critical evaluation of scientific claims, while maintaining enthusiasm for genuine discoveries and open-minded consideration of unusual possibilities. The goal involves fostering scientific thinking rather than either uncritical acceptance or reflexive skepticism toward new ideas. The fringe discussions surrounding 3i Atlas serve important functions even when their conclusions prove incorrect. They demonstrate public engagement with scientific questions, motivate more rigorous analysis of conventional explanations, and provide opportunities for education about how science actually operates when confronting genuinely puzzling observations. Future science communication about anomalous astronomical discoveries will benefit from lessons learned during the 3i Atlas media cycle. These include the importance of clearly labeling preliminary findings, providing multiple explanatory frameworks, and maintaining appropriate uncertainty levels while preserving legitimate excitement about potentially significant discoveries. The faithful adherence to various interpretations, whether favoring natural, artificial, or exotic explanations, ultimately served the scientific process by maintaining diverse perspectives and preventing premature consensus around insufficient evidence. This intellectual diversity, properly channeled through rigorous methodology, drives the kind of creative thinking necessary for understanding genuinely unusual phenomena. Epilogue: The Silent Giant's Legacy. As 3i Atlas continues its journey toward the outer reaches of our solar system, carrying with it more questions than answers. We find ourselves confronting a fundamental shift in how we understand our place in the cosmic order. This silent giant from interstellar space has forced us to acknowledge that the universe operates on scales and through processes that still challenge our most sophisticated theoretical frameworks. Whether the preliminary mass estimates prove accurate or require revision, whether the chemical anomalies receive conventional explanations or reveal genuinely new physics, 3i Atlas has already accomplished something remarkable. It has transformed interstellar object astronomy from curiosity-driven investigation into systematic scientific inquiry. The techniques developed to study this enigmatic visitor, precision astrometry campaigns involving hundreds of observatories, rapid response protocols connecting space and ground-based assets, and sophisticated chemical modeling of exotic volatile compositions, represent tools that will serve astronomy for generations to come. Every future interstellar visitor will benefit from the observational and theoretical infrastructure built around 3i Atlas. Perhaps more importantly, this object has demonstrated that the space between stars is not an empty wasteland, but rather a dynamic reservoir of material carrying information about planetary formation processes operating throughout galactic history. Each interstellar visitor represents a messenger from stellar environments. We can never visit directly, bearing chemical and physical signatures of conditions in alien solar systems billions of years ago. The planet seeding hypothesis, technological speculation, population statistics puzzles, and chemical mysteries surrounding 3i Atlas will continue driving scientific investigation long after the object itself fades from telescopic view. The questions it raised about ejection mechanisms, survival processes, and detection biases touch fundamental aspects of how matter moves through the galaxy and what that movement tells us about cosmic evolution. In a broader sense, 3i Atlas embodies the essential uncertainty that makes science compelling. We live in an era where astronomical observations can surprise us, where preliminary data can challenge established frameworks, and where the next discovery might revolutionize our understanding of how the universe works. That capacity for surprise, for genuine discovery, represents one of humanity's most precious intellectual assets. The media discussions, public engagement, and educational opportunities created by 3i Atlas demonstrate that scientific curiosity remains alive and well in an age often characterized by certainty and polarization. People want to know whether we're alone, how planetary systems form, and what secrets the space between stars might hold. These are fundamentally human questions that transcend disciplinary boundaries. As we prepare for the flood of discoveries that next-generation surveys will provide, 3i Atlas stands as a reminder that individual objects can still capture imaginations and drive scientific progress in unexpected directions. The transition to statistical analysis of large populations should not diminish appreciation for the unique characteristics that make certain visitors special. The legacy extends beyond astronomy into how we think about evidence evaluation, hypothesis testing, and the gradual accumulation of knowledge that drives scientific progress. 3i Atlas provides a case study in how communities respond to genuinely anomalous observations with excitement tempered by appropriate skepticism, speculation balanced by rigorous methodology. In the end, whether 3i Atlas proves to be a massive natural comet carrying exotic chemistry from alien stellar environments, a statistical outlier that appeared during humanity's first systematic interstellar surveys, or something even more extraordinary, it has already earned its place in astronomical history. It forced us to look more carefully at our assumptions, develop better observational techniques, and think more deeply about processes operating on galactic scales. The silent giant continues its journey back toward interstellar space. But the questions it raised and the techniques developed to study it will shape astronomy for decades to come. In that sense, 3I Atlas represents both an ending and a beginning, the conclusion of our initial reconnaissance of interstellar visitors and the opening of a new era in understanding our cosmic neighborhood. The next visitor might be even more puzzling, but we will be ready.